Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zaim Arif, and today we're going to be looking at Maxwell's equation and electromagnetic waves. Let's first look at the overview of this video. First, we're going to be looking at the introduction of this topic, and then we're going to dive deeper into the four equations of Maxwell's equation. Third, we're going to be looking at what is electromagnetic waves, and fourth is the real-life examples of electromagnetic waves. So in the 1800s, the understanding of electromagnetics had improved dramatically through many experiments and theoretical work. For example, Charles Augustin de Coulomb has established his law of electrostatics. André-Marie Ampère has published his fourth law. Michael Faraday discovered the electromagnetic induction through his experiments and proposed lines of force to describe it, and Emil Lenz solved the problems of the direction of the induction, and Franz Ernst Neumann wrote down the equation to calculate the induced force by the change of magnetic flux. But these experimental results and rules were not that organized back then, and sometimes it can be confusing to scientists to make further research about it. So a comprehensive summary about the electrodynamics principle was needed. So here's come James Clerk Maxwell. James Clerk Maxwell successfully summarized all the electromagnetic interaction using four elegant equations. First is the Gauss's law of electricity. So Gauss's law describes the relationship between an electric field and also electric charges. It says that any electric field points away from positive charges and towards negative charges. And also, in a Gaussian surface, the electric flux through a closed surface is proportional to the total charge enclosed by the surface. So the equation is as below, and this shows that electric field lines begins on positive charges and end on negative charges. So this is the first law or first equation in this Maxwell's equation. Second, he wants to talk about magnetism. So he takes inspiration from Gauss's law of magnetism, which states that the electric charge have no magnetic analogues or monologues. He says that magnetic poles do not exist as monopoles. This makes sense because any magnets that we have, it always have two poles, that is the north pole and also the south pole. Magnets don't exist just in one pole, just north pole, just south pole. It does not exist. It must exist as both. And he states that, and he takes the equation of the net magnetic flux through any closed Gaussian surface and equate it with zero. Any magnetic flux through a closed surface must equals to zero. Now, this shows that the magnetic sources are always dipoles, and magnetic field lines are a continuous loop that never begin or never end. Why does the net magnetic flux equates to zero? So imagine this. Magnetic field lines are a continuous lines going in a loop that never begin or never end. So in any closed Gaussian surface, let's take a sphere for example, any lines that comes out of it must also comes in back into the south pole, going out of the north pole back into the south pole. So that makes it the next flux equals to zero, as stated here. And third law is taken from the Faraday's law. So Faraday's law of induction describes how a changing magnetic field will induce an electromotive force that produces current. So the electric flux through a closed surface is proportional to the total charge enclosed. The rate of change of magnetic flux have a relationship with changing electric field. And fourth is very interesting law. It's about Ampere's Maxwell law. So it was taken from Ampere's equation that relates magnetic field and electric current. So in the original law, Ampere states that the flow of current through a wire induces a magnetic field around the path surrounding a wire. So let's take a look at this. imagine we have a wire here and a current flowing through it in the inside. Okay, this is current. So whenever current passes through a wire, it generates magnetic fields. So there is a magnetic field here, here, and also here. So this is all the magnetic field that is generated by a flow of current in a wire, and it is given by this equation. Now what makes this interesting is that Maxwell thought of this before, that okay, imagine we have a circuit set up as figure here, where a source of EMF is connected across a parallel plate capacitor, so that a time-dependent current develops in the wire. What this means is, okay, if we have an empty capacitor, the flow of current will not be constant, it will change depending on time. So we want that changing current, we want that time-dependent current. So this is why we set up this circuit as shown. And suppose we apply Ampere's law to the loop here, shown at time before the capacitor is fully charged, as I mentioned before. So there are a changing current, or a flow of current going on here. So if we apply that law, Ampere's law, we can see that on the surface here, S1, there will be a magnetic field generated according to Ampere's law, because the current can flow through the wire or through this surface here. So it will generate an magnetic field here, given by this arrow here, B. But when we come to surface 2, we don't observe any magnetic field according to Ampere's law. So this is the flaw of Ampere's original law, which Maxwell thought of it. So this is the equation. If we have a flow of current in S1 just now, we will see the production of magnetic field. But if there is no current, because capacitor cannot let charge pass through this gap, because there is a gap here filled with air or any other material in the capacitor, so current cannot pass through this gap. So when there's no current, there's also no magnetic field according to the original Ampere's law. So Maxwell thought of it, and he decided to just, let's create a new current that is called a displacement current to complete this equation. And he comes up with this equation, which adds this displacement current to make the law complete. Now, after Maxwell have established his 4 equations, he realized that this existence of this 4 equation implies the existence of waves made up of oscillating electric and magnetic fields. So a changing electric field produces magnetic field, and a changing magnetic field also induces an electric field, as stated in equation 4. And this cycle continues as the wave propagates through space. And these electromagnetic waves, Maxwell have done calculations and all, and he says that these waves travels at a constant speed given by this equation, which is C equals to 1 over permittivity of free space, that equates to 3 times 10 to the power of 8 meter per second. And coincidentally, this is the value of speed of light, which confirms that the light itself is an electromagnetic waves. Okay, now let's understand this better. Imagine we have an alternating current that passes through a metal rod. So when there is a changing current here, it will produces a magnetic field. Okay, and the changing magnetic field will induce another changing electric field. The changing magnetic field creates an electric field E naught. So this is due to Faraday's law, which states that a changing magnetic field induces electric fields, and this field form a closed loop due to mathematical symmetry of Maxwell's equation. And now we have this changing electric field E naught that is generated by the first magnetic field generated by the flowing or the changing current here. According to Ampere's law, a changing electric field will create a new magnetic field. So this electric field form a new magnetic field besides it. So when there is a changing, it produces another field, another electric field, and then produces another magnetic field. So the whole process continues like dominoes falling. And as we can see here, the first magnetic field, where the changing magnetic field produces a changing electric field, and then creates a new changing magnetic field, and so on and so forth. So this creates a self-sustaining chain reaction. Next, this is a visual representative of how the wave propagates through the space. So electromagnetic disturbance moves outwards from the source. So imagine this is the force. It moves this way outward, and then it moves together with the magnetic field that is perpendicular to each other. So they carry each other through the empty space. And now we're going to see how these electromagnetic waves are applied in the real world. So the closest thing that I can think of is our antenna. So a practical example, antenna is a practical example of electromagnetic wave generation. So we're going to look deeper right now how antenna works. So antenna consists of two conductive rods that is connected to an alternating current AC. And as we know, AC current generates a changing directions of current. So as current alternates, the charge on the rods also switch between positive and negative. So we can see here from positive to negative, and then it changes as time goes by. And this is the electric field that is produced in the rod. So we can see that it oscillates between positive and negative, and then back to positive. So this changing of electric field also generates a changing magnetic fields. So this is how it looks like, and both of these field will detach and propagate through space as electromagnetic waves. So these waves can be then received by another antenna source some distance away, converting them back into electrical signals. So imagine we have a radio tower here, generates electromagnetic waves, and then another radio tower here receive that and then change back to electrical signals. So this is the foundation of wireless communication, from radio to television, Wi-Fi, and satellite links all uses this electromagnetic waves equation by James Clerk Maxwell. So that is the importance of his work, combining all of the equations all together, the knowledge about Gauss's law of electricity, about the magnetic fields, about magnetism, and he combined all of it into 4 beautiful equations, which then can be used by us today to make a new technology. As we can see here, we have 5G and all of that. So that is the practicality of his contribution to today's world. And that is all from me. Thank you so much.